And in this talk, we will see use of signal processing and machine learning for analysis and classification of ECG signal, electrocardiogram signal. And then if time permits, then we'll go for multi-channel signal processing also. There are many scenarios in real life where actually we use multi-channel data, and our group has developed some signal processing techniques to analyze this multi-channel data. And we have combined them with machine learning algorithms to process this multi-channel data. And for the application, we have like brain-computer interfacing and schizophrenia diagnosis that has been done. But similar kind of concept can be applied for multi-channel ECG. So various applications will be presented, and it will explore many directions where participants can explore these methods for various applications. So with this background, let me share my slides. Professor Hemant?
Yes, sir.
Not able to share. Now it is coming up.
Sir, it's coming now. Slide has come. Advanced signal processing for ECG signal analysis
Yes,
and classification.
okay. So thank you. Good afternoon, everyone. So today's talk is on advanced signal processing for ECG signal analysis and classification. And in this talk, we will see use of signal processing and machine learning techniques. And signal processing here, we use advanced wavelet transform. And we have studied various cardiac disorders, this diseases, heart diseases, and where this ECG signal can be used. And we'll see how this signal analysis and machine learning techniques can be useful to design automated systems which can detect abnormal ECG and which can be associated with various diseases. So motivation comes from these regions, cardiovascular diseases that we call CVDs, and number one cause of the death. Actually, you know daily life every time we listen, somebody has died from silent heart attack, from this disease, coronary artery disease, congestive heart failure. So many, actually this is one of the number one cause of death. And every year 17 million people die due to cardiovascular diseases. So the mortality rate due to cardiovascular diseases are 272 per 1 lakh people in India, and 235, that is number, per 1 lakh population globally. So you can see in India, actually we have large number compared to global. So that actually in India, cardiac disorders, heart diseases is actually very serious concern. And common heart diseases include coronary artery disease, myocardial infarction, congestive heart failure, and atrial fibrillation. So electrocardiogram signal that we call ECG is commonly used signal for diagnosis of these disorders, and a computer-aided diagnosis system is required where there is a lot of use of signal processing, feature extraction techniques, and machine learning methods. So the objectives of this work, our work as follows. To develop an automated detection method which is based on flexible analytic wavelet transform using heart rate variability signals. And sometimes, like in ECG, we have PQRST pattern. So each different regions, they are clear from the signal. But when you have noisy scenario, like you want to detect heart disease in the field, then actually this PQRST pattern, they are sensitive to noise. The time domain representation is sensitive to noise, so that is lot of effect of noise. So in order to carry out disease detection in field or away from the out of the hospital, then there is actually use of heart rate variability signal. So heart rate variability HRV signal that we obtain from the RR peak by using some computation, and from RR peak we get heart rate, and heart rate as a function of time when plotted, then it becomes heart rate variability, HRV. So that actually that also we use for a scenario where this recording is not taking place in the hospital. And we develop automated diagnosis method for coronary artery disease based on flexible magnetic wavelet transfer using ECG signals, and to develop an automated identification method for the myocardial infarction ECG signals using FAWT framework, and to propose a computer-based approach for the automated diagnosis of congestive heart failure patients based on the FAWT, that is flexible magnetic wavelet transfer using heart rate variability signals, and to develop a computer-aided identification method for atrial fibrillation ECG signals using FAW. So these are all actually methods will be explained in this talk. So first part actually of this talk is automated detection method for normal and coronary artery disease heart rate variability signals using flexible analytic wavelet transform. So coronary artery disease, if you see, it actually it affects the metabolic activity, and the heart muscles get weaker with time. And here you can see this normal artery and this narrowing of artery. So with age, so this will become narrow, and the lipid deposit of plaque, and due to that actually there is problem in the blood circulation. So that actually that can blocks occurs, and this can result in coronary artery disease. So in many cause arrhythmias and heart failures, it may cause this arrhythmias and heart failures also, and timely diagnosis is essential. Otherwise, actually, person can die also. That is, we have to save life. So, timely treatment is very important. And coronary artery disease cases data recording itself is a challenging part. Even many patients die before actually reaching to the hospital. So, our methodology that actually this is a proposed methodology. We have heart rate signals. Then heart rate means heart rate variability signals, and then if we use flexible analytic wavelet transform based decomposition, then we extract set of nonlinear features. Then these all features are not actually useful, so we select significant features. This is where this is not a ranking of features. Then we ranked features are given as input to classify. Then actually it will classify this coronary artery disease normal classes. So data acquisition and pre-processing part. The ECG signals of 10 healthy subjects and 10 coronary artery disease patients. They have been recorded at Equara Hospital, Calicut, Kerala, India, and BioPAC equipment was used. And sampling rate was 500 Hz, and noise removal was done using bandpass filter whose lower cutoff frequency is 0.3 Hz and higher cutoff frequency 15 Hz. RP identification is done using Pont-Tompkins algorithm, and 82 heart rate variable signals are used, where H heart rate is defined as 60 upon TRR. TRR means this is time interval between consecutive RRPs. So this is a ECG signal, plot of ECG signal. You can see this is like 1, 2, 3, 4 beats, and RR interval is defined between the time interval between two consecutive RRPs. And if you inverse that and multiply by 60, then you get heart rate, and you plot heart rate as a function of time, then it becomes heart rate variability. So now heart rate variability, if you see for normal case and for abnormal case, coronary artery disease, so you can see this heart rate variability for normal person, there is no significant changes. The rate is nearly same. On the other hand, if you see heart rate variability for coronary artery disease, the abrupt changes are there. So that actually now this information we want to integrate with the features signal. This is the purpose of signal processing, to summarize this information in terms of features. So which way we can use for the diagnosis purpose. So many this wavelet transform actually have been proposed in the literature. So like conventional wavelet transform that we have seen, that is actually based on the mother wavelet is fixed. And once you have mother wavelet, then we design a low pass, high pass filter, downsample by like that. And upsampling, downsampling are also fixed. So this flexible analytic wavelet transform, that is actually advanced version of the tunable Q wavelet transform, where you have flexible Q. Flexible actually now here wavelet parameters are there based on the different Q. You can design actually different mother wavelet. So you have flexibility to change the mother wavelet you can have flexibility to change the upsampling, downsampling. So this is flexible. That is why we can call it flexible analytic wavelet transform. And here actually analytic part is coming because it has low frequency signal, low frequency part, and high frequency part has actually two kind of information. This positive part and negative part, that high frequency. In this work, we have actually modified that FAWT, and so that it can be used as a conventional wavelet transform. So you have approximation and detail. There were two details in the conventional FAWT. So what is suggested, whatever details you have to, you obtain the outputs and then you combine all of them, both of them, and you will get single output detail. So that in that way, actually every stage you will have one approximation and one detail, so that we can use this flexible analytic wavelet transform like a conventional wavelet transform, but with all desired properties, with a flexible mother wavelet, with flexible upsampling, downsampling, etc. So FAWT provides facility to analyze the signals with the easily adjustable parameters P, Q, R, and S. So here you can see the signal Xn, and this upsampling, and then low pass filter, high pass filter, and then it's conjugate, and your up downsampling also. So then you have, this is approximation signal, this is detail. So both detail are combined. First subband signal is reconstructed from the detail coefficient of this level. Similarly, we have done for all levels. So in that way, each level you have one approximation and one detail. So this is like, if you go for jth level of the decomposition, then actually you will have j details and one approximation. So like that, j plus one subband signals will be there. Out of that, one approximation and j details will be there. So this is one example for a third level FAWT based decomposition of heart rate variability signal. First one is case of normal, second one is coronary artery disease. So here you can see this third level decomposition. So you have one approximation, three details for this normal heart rate variability signal. And the coronary artery disease case, you can see this approximation and three details. So now actually third level, when you see this, each subband shows the difference. So this difference actually we want to summarize in terms of features. And then we parameter selection of FAWT is important part. So for signal, this S to R ratio, if greater than equals to 3, then basis of FAWT source oscillatory nature. This is actually from the literature. And in order to control the oscillations, the ratio of S to R must be less than 3. So that actually, like if you say S equals to 2 and R equals to 1, so then actually like equals to 3, that can be, by choosing S and R values, one can satisfy this condition. To achieve better frequency resolution, the ratio of P to Q must be between 0.5 and 1. And so we have selected P equal to 7 and Q equals to 8. So ratio of P to Q will be 0.875. And this beta should be between 1 minus P to Q and R to S ratio. So beta is actually 0.4. So here now parameter selection of FAWT. You can see if you have ratio H to R 3 and ratio H to R is 2. So if you have ratio actually greater than this 3, then there is ringing effect, oscillatory nature. On the, if you have ratio H to R equals to 2, by that actually you are able to design wavelet which is compact support. So that time limited nature is there. There is no ringing effect, there is no oscillatory nature. So that is effect of parameter selection on the mother wavelet. So according to your requirement, one can actually design mother wavelet based on the selection of parameters. So the features, first feature that we have studied, that is K nearest neighbor entropy estimator. So it is based on the distance of sample from its kth neighbor, and it quantifies the degree of scatter. So here this is a mathematical expression for computing this K nearest neighbor entropy estimator using d gamma function, and that is actually derivative of log of gamma function. Other parameter is fuzzy entropy. So it is a measure of the regularity of heart rate variable time series, and that mathematically can be expressed by this for these two formulas, where SJKE is the degree of similarity and computed using fuzzy function, and F and G control the boundary of the fuzzy function. So if E equals to 5, F equals to 2, and G equals to 0.3. That is like. So feature ranking and classification. So this is feature ranking methods that includes Wilcoxon method, entropy method, receiver operating characteristics method, Bhattacharya algorithm. After that, this least square support vector machine, LSSBM, that actually used this is the mathematical expression for LSSBM. And kernel functions which we have used, radial basis function RBF kernel, whose mathematical expression can be seen here in this slide, and Morlet wavelet kernel function whose mathematical expression can be seen here. So now we will see results. So p values of the features computed at j equals to 3. So if you j equal to 3, then there will be four subbands A3, D3, D2, D1, and KNN entropy estimator and this fuzzy entropy. In both cases, if you see probability, then we have seen actually this probability value that is actually at second level. If you see, that is actually this is the p value of the different computer equals to 3. So in all actually like lowest probability value that has been considered. So like this is this fuzzy entropy, second level, third level for the different values of j. Okay, so sorry, this is. So here, this is actually p value of the features computed equals to 3. And here, this p values of the features computed different values of j, second, third, fourth, fifth. So we have actually computed from the approximation signal. This is D1, D2, D3, A3. So this, that p value, so second level, this approximately the p value comes out this, and the value which we have taken like as lowest p value that has been used to detect to find out the number of level. So based on that, if you see that actually third level has been used computed here. So that is the lowest probability value. This lowest probability value, according to that third level is selected, and third level we have computed this D1, these are the decompositions. So this is subband signal D1, D2, D3, and approximation. So these are the features. So mean and standard deviation of the computed features can be seen here. This is feature KNN entropy and fuzzy entropy. And here the subband third level. So third level approximation details D1, D2, D3, and this fuzzy entropy also. So for a normal class and coronary artery disease class, mean and standard deviation, that features can be seen. And it is clear that that actually they are they are covering different range of the features, so that actually normal and coronary artery disease both classes can be separated out. So this is more clear from the box plot showing the ranges of the features for k-nearest neighborhood entropy and fuzzy entropy that you can see for this third level. So this is approximation, normal and coronary artery disease, the third level detail, second level detail, and first level detail. Similarly, fuzzy entropy, that is actually third level approximation, third level detail, second level detail, and first level detail. So first one is for KNN entropy, and second one is for fuzzy entropy. And here this plot showing the accuracies for different number of features, Morlet, wavelet kernel, and RBF kernel. So like number of features, the accuracy of classification, Wilcoxon, Bhattacharya, ROC entropies ranking methods. And similarly, this Morlet RBF kernel case, this plot accuracy of average accuracy of classification versus number of features for different rank method, Wilcoxon, Bhattacharya, ROC entropy. And you can see different number of features. Actually, they actually have maximum purpose. So if you see number of features are 4, that gives you the best classification performance. So we have compared this proposed method with other existing methods which have been studied for this database or similar kind of database. So Lee and others 2007, they used HRV and linear nonlinear methods with 6 linear and 5 nonlinear features and support vector machine classifier. They got 90% classification accuracy. And Jiao and Ma and others 2008, they use hard sound signals, empirical mode decomposition and trigger energy operator and various statistical features backpropagation neural network classifier. They got 85% classification accuracy. Babagulu and others 2010, there is exercise stress test, genetic algorithm and binary particle swarm optimization with 23 features and SVM, the whole vector machine classifier, is got 81.46% classification accuracy. And Dua and others 2012 with HRV and principal component analysis, 6 nonlinear features, multi-layer perceptron classifier got 89.5% classification accuracy. Viria 2030, there is heart rate variability, discrete wavelet transform, principal component analysis, there is 10 features, Gaussian mixture model, they got 96.8% classification accuracy. Partidar and 2050, heart rate variability and tunable wavelet transform and principal component analysis, they got 2 quantum features. With LSSUM classifier, they got 99.72% classification accuracy. In the present work, heart rate variability and flexible anti-wavelet transform, the scale and entropy estimator and fuzzy entropy has been used as features with least square support vector machine classifier, and this, for this database 100% accuracy is achieved. After that, we have proposed an automated diagnosis method for coronary artery disease patients using ECG signals based on the flexible analytic wavelet transform, and this is the proposed methodology. We have raw ECG signal, then noise and baseline bounded removal is performed. Then we have performed segmentation of ECG signal into beats, and the decomposition of beats using FAWT is carried out. Then we compute this cross information potential from the real coefficient. And here that I mentioned earlier, there are 2 details because this is an ideal transform, so we have taken advantage of that. And between these 2 details, we have computed cross information potential that has been used as a feature. Then classification is performed using least square support vector machine with RBF and knowledge wavelet kernels, and then actually we classified into normal and coronary artery disease classes. So database Saint Petersburg Institute of Cardiological Techniques database is used. It has Fantasia open access database, 40 normal subjects and 7 coronary artery disease subjects. Sampling rate is normal ECG signals 250 samples per second, and coronary artery disease ECG signals is 257 samples per second. Baseline wander and noise elimination has been done using Duvechi 6 basis function of wavelet and R-peak detection using Penn-Tumkus algorithm. ECG beat is a segment of 116 samples, and then total number of coronary artery disease ECG beats, they are 44,426 numbers, and normal ECG beats, they are in 1,37,587 numbers. So here you can see this is normal ECG and this beat, and this is abnormal ECG, the coronary artery disease. So this actually, now this changes in abnormal beat, ECG beat, we need to detect with the signal processing. That is actually purpose of signal processing. So we have decomposed this coefficient using this FPWT based decomposition for ECG beat for CAD and normal cases. So here you can see this for each like level, like there are this is 4 level decomposition. So there will be 5 4 level decomposition. There are 4 details will be there, and if you 5 level decomposition, 5 details will be there. So each is 5 level decomposition. So each level you have 2 details. So that we have computed cross information potential between the first level, second level, third, fourth, and fifth level, like that. And that is actually for normal case, and this is for abnormal case. So cross information potential is computed between the values of detailed coefficients, and it can be estimated using kernel-based approach, which you can see mathematical expressions. And it is based on the Gaussian kernel that is actually defined as by these expressions. If you use this one here, then it will this crossover potential. So we have seen this 5 level of decomposition. So mean and standard deviation of CIP features, level of decomposition 1, 2, 3, 4, 5. Then cross included D1, D2, D3, D4, D5. And then this is coronary this is mean and standard deviation value. For normal case, this is a mean and standard deviation value. Probability value is less than 0.0001. So that is actually, so these ranges, they are features, they are statistically significant because the probability value is coming out less than 0.05. So now we'll see results of the classification of different level of decomposition using different kernel functions. So level of decomposition first, second, third, fourth, 5, and each level we applied RBF, Morley wavelet, RBF model, this and accuracy. You can see here accuracy and sensitivity, especially using different kernel functions. And now, how this accuracy, sensitivity, specificity, these performance measures vary with number of folds. We have used 10-fold cross validation. So 10-fold means we have features, and features are divided to 10 different parts. 9 parts are used for training purpose, and 1 remaining used for testing purpose. And this we do for all 10 times, different times, and that we take average. So we will, that is 10-fold cross validation accurate performance. And here you can see different actually fold, different time, this accuracy changing. And so same is for first one is for RBF and second one for Morley wavelet kernel. So then we have compared our method with other methods for coronary artery disease. Acharya and others 2016, they use ECG signals, higher order statistics, 31 cumulative features, and recently classified, and with 10-fold cross validation, we got 98.99% accuracy. In the present work, ECG signals are used, and with flexible analytical transfer cross potential, LSSBM classified with 10-fold cross validation, 99.60% classification accuracy is obtained. Now, other part that we have done, that is automated identification method for normal and myocardial infarction ECG signals using FAWT method. And myocardial infarction is a condition which indicates the injury of the heart cell. And doctors use the ECG signals for diagnosis of this myocardial infarction. And myocardial infarction results in the ST deviations and T wave abnormalities in the ECG signal. So only 82% ST segment elevation in MI subjects may be recognized by the experienced cardiologist. So there is actually there is need of machine learning signal processing based technique to detect these changes. So this is the proposed methodology. We have MI ECG beat and normal, and then we actually this we want to classify. So for the ECG signal, we pre-process it and segment ECG into beats. Then beats are subjected to FAWT, and then we obtain subband signal 1 J plus 1. Then we compute sample entropy from each subband. Then from that actually perform the classification in terms of normal ECG beat and MI ECG beat. So data acquisition and pre-processing part is PTB, a diagnostic ECG database is used, and sampling rate is 1000 samples per second. Normal subjects, there are 52 subjects, and MI subject there are 148, and 236 wavelet basis function is used for denoising purpose, and the pen temperature algorithm is used to identify the R peaks. So now total MI ECG beats we have 40,182, and normal ECG beats we have 10,546. So here you can see these two beats, normal and myocardial infarction. And that actually, you can see a lot of distortion in the MI beat, that is ECG beat, due to the myocardial infarction. So now we perform this FAWT based decomposition. So if you have here, for example, 5 level of decomposition, then you have 6 subbands for normal, a 6 subbands for myocardial infarction. And then we have actually features and classification part. Sample entropy measures the complexity of the time series. It improves the performance by excluding the bias due to self matches counted in the computation of approximate entropy. So we have used random forest classifier and least square support vector machine in this work to classify the normal and myocardial infection ECG beats. So now you see the accuracy is a function of R and the function of J. So this R we have selected based on the highest performance, and when you are selecting number of levels, then actually it is when you increasing, then it is the accuracy is also increasing. So we have selected the highest possible number of level of the decrease. So that is 24. So when you 24, there will be 25 subbands. So in this table, we see mean standard deviation of the computed features for all 25 subbands, and then using normal class and myocardial infection class. They cover actually different range of features. And then classification accuracy for unbalanced data set using LSSW classifier. So we unbalanced, they have different number of signals, but other case actually we have made it balanced, same number of signals. So then kernel functions are linear polynomial RBF knowledge wavelet, and parameters that's x equal to 2x3, they are trial and error based, they are selected. And then accuracy, sensitivity, specificity can be seen in this table. And similarly, for the balanced data set using LSSW classifier, we can see different kernel functions, parameters, and accuracy, sensitivity, specificity. Then we have compared our method with other existing methods for myocardial infection detection. RF and others 2010 in time domain method, number of leads 12, and back propagation network with 97.5% classification accuracy achieved. Banerjee and others 2014, they use cross wavelet transform based method, and number of leads 3, threshold based classifier is used, 97.6% classification accuracy achieved. And Liu and others 2015, they use ECG polynomial method with 12 number of leads. So this decision declassifier got 94.4% classification accuracy. Sharma and others 2015, they use multi-scale energy and eigenspace based method, number of leads 12, and SBM with RBF kernel class, they use 96.15% classification accuracy. Acharya 2016, they use discrete wavelet transform nonlinear method with one lead nearest neighborhood classifier, they got 98.8% classification accuracy. Acharya 2017, no feature extraction selection, they used one lead 2, and deep learning method, they got 95.22% accuracy. So you can see here, same database, deep learning is giving less, and the simple classifier is giving better. So it is not always true that deep learning will give better performance. So present method with FAWT and sample entropy with one lead data ECG, we have used least square support vector machine with RBF kernel. So it is 99.31% classification accuracy. After that, we have proposed computer-based method for the diagnosis of congestive heart failure HRV signals using FAWT. And nearly 16 to 26 million people are living with congestive heart failure globally, and heart is unable to provide sufficient blood supply to fulfill the requirement of the body. So dyspnea, edema, and fatigue, these are the common symptoms of the congestive heart failure. And congestive heart failure patients are more susceptible to sudden cardiac death. So there is actually need of the automated method which can detect disease in the advance. So now this is a proposed methodology. We have HRV signal, heart rate variable signal, they be decomposed using FAWT method. Then we have suggested use of actually adding subbands. So different skills are combining all subbands. So adding subbands from high frequency to low frequency. And other structure is adding subbands from low frequency to high frequency. So then we compute atrial fibrillation entropy and this permutation entropy, accumulated permutation entropy. And then actually this is all features are not useful, so we have ranked useful features, significant features, and then classify using LSSW classifier. Then we have normal and congestive heart failure classes. So data set, we have obtained R interval directly database from the PhysioNet, and CHF patient 15, for normal survey are 40, Fantasia, and for this Bath Israel Disumis Medical Center, VIDMC. So CHF is a normal subject, we have 80, MITVH normal sinus rhythm, and congestive heart failure HRV segment, there are 3,212, Normal HRV segments, MIT VI, they are 3,420, and normal HRV segments, when they see are as 500. So this actually we have combined together. And now RR interval signal, here you see, initial HRV, we have used RR interval signal. So this is for normal case, and this is for congestive heart failure. So you can see normal, it is showing variations, and congestive failure, it is showing impulse spikes. So now here, this FAWT based decomposition, now for this RR interval signal, so this 5-level decomposition. So you have one approximation, 5 details for normal case and congestive heart failure case. And then this feature permutation entropy, and this is mathematical expression for permutation entropy, and fuzzy entropy, that is all explained in earlier section. And then actually this accumulated permutation entropy and this similarly accumulated fuzzy entropy can be computed over cumulative sums of subbands. So this accumulated permutation entropy defined by this expression, and the accumulated fuzzy entropy defined by this expression. And where SI can be SLI, SHI. So low to high, high to low. So these are the signals at different frequency scales and the combination of used subband signals. So signal at different frequency scale, SL1, SL2 to SL5, and these are accumulated subband signals. So this is low frequency, low to high, like that. And signals at different frequency scale, SH1, SH2, like this. Now this is lower signal different frequency scale, so low to high, and here high to low, like this. So D1 and then D1 plus D2, so high to, we are going low side. This is low to high side. So in that way, actually, we have done this scaling operation. Now we will see accuracy in terms of percentage of the features for the different kernels using with LSB classifier. So features, accumulated fuzzy entropy, accumulated permutation entropy, sequence length, this is required outcome entropy, linear RBF and Morley wavelet and polynomial kernels. And if you see in this Morley wavelet kernel function, accumulated fuzzy entropy is given 96.29%, is highest in one. Similarly, accumulated fuzzy permutation entropy 91.39%, which is for Morley wavelet. So that is higher. Now we have combined, actually, we have studied this mean estimation of computed features, accumulated fuzzy entropy, accumulated permutation entropy for different scales, and low to high, high to low, and then actually it's congestive heart failure class, normal class, and you can see different range of the features. Similarly, accumulated fuzzy entropy is low to high, high to different range of the features can be seen here. Now we will see classification performance of the computed feature using LSB classifier, unbalanced dataset 1, unbalanced dataset 2, and balanced dataset 1, balanced dataset 2. Kernels are Morley wavelet, polynomial, RBF linear, and parameters they are selected based on trial and error. Number of features are given in this row, in this column, and the specificity, sensitivity, accuracy can be seen in this table based on these actually kernels, parameters, and the studied signals. Then we have compared our method with other existing methods in the literature. So Pekisia and others 2011, they use time and frequency domain based parameters. DCMT classifier, the number of features 9, and they got 96.4% classification accuracy. Zhong and other 2011, they use DFA based parameters with support vector machine classifier, number of features are 15, and then 94.4% classification accuracy. You and others in 2012, the time and frequency parameter SVM classifier got 16 number of features, 96.15% classification accuracy. Narin and Russ in 2014, they use only the parameters and wavelet based measures. We support vector machine classifier. Number of features are 27 and often accuracy 98.8%. Acharya 2016, they use EMD and 13 only the parameters, support vector machine classifier, number of features with this database under unbalanced dataset 1, unbalanced dataset 2, balanced dataset 1, balanced dataset 2. So it can be seen the accuracy. Present method, that is FAWT based accumulated entropies, LSSB classifier, the number of features, and unbalanced dataset 1, unbalanced dataset 2, balanced dataset 1, balanced features, accuracy can be seen. So our proposed method actually, gives the better performance than the other existing methods in the literature. And this another method that actually we have proposed, that is computer-aided methodology for identification of normal and atrial fibrillation ECG signal. So atrial fibrillation characterized by the irregularity of atria contraction. A number of people having atrial fibrillation is double in 40 years. The death rate of the atrial fibrillation patient is double as compared to the normal subjects. So dyspnea and fatigue are the common symptoms, and electrocardiogram ECG is widely used for the diagnosis. So this is the proposed methodology. We have ECG signal reprocessing, then we extraction of a small segment of ECG signal. So now initial beat, we extract small segments and decomposition of segments using FAWT method. Then we compute permutation entropy from decomposed subband signals and computation of the log energy operator, this Lyapunov exponent, this log energy entropy from decomposed subband signals. And then we perform classification using this normal and atrial fibrillation. So data set, we have the MIT BIH atrial fibrillation database, which had 23 atrial fibrillation patients and 250 samples per second. And atrial fibrillation, AFL, atrial fibrillator, JAB, gestational rhythm, and all the rhythms. These are the actually included categories, types for this in the considered database. And so now we have 243 normal and 247 AFIB systems. DV6 wavelet basis function is used for delousing, and now total we have 17,267 atrial fibrillation ECG segments and 1,14,214 normal ECG segments. So now we can see plot of these segments of ECG segment for two classes, normal and atrial fibrillation. Atrial fibrillation, that actually these signals are distorted, and that distortion actually needs to be needs to be detected by signal processing algorithm. So these are the decomposed FAWT based decomposition, decomposed 5-level decomposition. So we have one approximation and 5 digits, 1, 2, 3, 4, 5, 6, 5-level decomposition. For normal case, this is atrial fibrillation case. Log energy entropy is computed using this expression, and the permutation entropy is already explained previous. So this mean and standard deviation value for log energy entropy and permutation entropy features can be seen in this table. So this for 6 subbands, mean and standard deviation is for atrial fibrillation normal classes. In same permutation entropy for these subbands can be seen in mean and standard deviation. So different range is covered for different actually subbands by using different features. Now classification performance of random forest classifier at various decomposition level of FAWT. So feature is log energy entropy, permutation entropy, and number of level J here. So total features can be seen in this table, and accuracy in terms of percentage, sensitivity, specificity, that actually can be seen in this table. Now classification performance of DCNT classified at various decomposition level. So for the all features, we have studied these 2 features, number of levels and total features and accuracy, specificity, and this can be seen in this table. And then classification performance of random forest and DCNT classifiers at various decomposition levels with the combination of log energy entropy, permutation entropy features. So we have classified random forest DCN3 and number of levels 5 and 10. Total features and accuracy, sensitivity, specificity can be seen here in this table. And then we have seen 10-fold cross-validation process, each fold the performance of classification by using this random forest DCNT classifier. So it can be seen that random forest is giving better performance. And then we have compared our method with other existing methods in the literature. Tatanio and Glass and thus learned one, they use MIT BIH AFDB database, RR intervals, delta RR intervals, Kusto statistical test, and they got sensitivity 94.40%, specificity that is 97.0. So there are different methods, and our present method that is based on MIT BHE FDP database, ECG signal law energy entropy and permutation entropy features. And in all, we have accuracy, sensory specificity. In these terms, our method is giving better performance compared to our existing methods in the literature. So this is the conclusion of this entire talk. A FAWT-based automated detection method for coronary artery disease is developed using heart rate variability signals. The method yielded maximum classification accuracy on the study database. Automated diagnosis method for coronary artery disease using ECG signal developed. The performance of the proposed method is found better than the other method studied in the same database. A method for automated identification of MIECG signal using FAW developed. That method achieved better classical performance as compared to the reported work. In computer-based approach for the automated diagnosis of congestive heart failure patients developed, our proposed system has obtained better performance than the compared work with a smaller length of the HRV signals. The computer-aided identification method for atrial fibrillation ECG signals using FAW developed. The performance of the proposed method has been compared to the other is comparable to the other methods. However, RP and P wave detection is not required in our method. So this actually this talk is based on the following publications. So I request participants to go through these papers in order to have detailed information about the presented work. Thank you very much.
Hello. So if participants has a question, you can please ask. Sir, thank you, sir, for a nice talk, sir.
Yeah. Yeah, thank you, Professor Hemant. Thank you for the opportunity. Thank you very much.
No, sir, it's our pleasure, sir, that you person, sir, like in signal processing, sir, you subject make it a very simple and that how can we, sir, publish the work. In research, especially, sir, your contribution is awesome, sir. I want to share to the participant that an interview, during my interview, when many members have asked many times that, okay, you are working with Professor Pachori, so why don't you have so many publications? So this is a common question. Sir is that much well
Thank you
known.
very much. I will actually uh, this 1 hour talk. Could you please arrange tomorrow? I have to leave for that actually. So no.
Okay, sir. Okay, sir. No problem, sir.
Thank you very much. Okay, thank
Okay,
you very
sir.
much, everyone. So tomorrow again for 1 hour I will deliver talk and I will take all of your questions.
Okay, sir. Okay.
Thank you. Thank you.
Okay, sir. Thank you. So, Ruchi, you asked the question, which techniques we use for classification of EEG data, DL techniques or SVM and other techniques, which one is best? Actually, sir will join us for, as I told you, see that he is already facing some issue. So see, tomorrow, as sir is leaving for that emergency work. So tomorrow we will address the question. As I told you, if you can either you can keep the question with yourself or you can email to me or him or either keep me in the CC when you are mentioning about the FTP. So this is regarding. So now we will take up the break and we will start after 10 minutes, right? So regarding a new topic, that is basically the I will take up that session. That will be regarding basically the technique which has benefited me a lot. That is basically graph signal processing. So that we will start in a 10 minutes. So just we have the break. But please be there, right? Because many concepts are many applications. Because once I will introduce you the GSP and today and tomorrow, and then we will see the applications of it. We will join at 4:10.